I will.不大行。Okay, we're going to start today. I'm a little bit, my voice is a little bit coarse, so I will try to speak very softly and maybe very shortly today. I will make the class may be a little bit shorter today than usual. Today, there will be a two lecture series on ensemble empirical mode decomposition. When we developed this method, I was still working for NASA. So as a almost a practical joke, we also named this as a noise-assisted signal analysis, short for NASA. Yeah. This, actually, the whole thing is discussed in this paper published in 2009, called Ensemble Empirical Decomposition in the Advances in Adaptive Data Analysis. What I'm going to do today is to give you a preliminary, give you the why and how this method was developed. Yeah. And the method itself will be introduced next time. Can you hear me, by the way? Our colleagues in Tokyo, can you hear me?
Yes.
Okay, all right. So I cannot speak. Yeah, I cannot speak louder today. Yeah. In the previous sessions, we have discussed the intermittency, and the intermittency actually is a very good method. However, we have to introduce a subjective criteria for intermittency tests. To implement intermittency, we have to say, I'm going to cut off those wavelengths longer than certain preset criteria. So I'm looking for high frequency here and there, everywhere. We'll do that. But the intermittency has really relieved some of the mode mixing problem. But then, because you have to set you have to choose a criteria. That selection of that criteria actually is subjective. That means I have to make a decision. That decision is independent of the data. And because of that, it's no longer totally adaptive. Yeah, because this decision, you made it. We'll come back to that. Now, however, then we find that if we apply EMD to study white noise, we find EMD when applied to white noise, actually the white noise itself establishes a very uniform frame of scales. This we will discuss. I just want to give you an overall picture. So this frame that gives you the uniform scale over the whole range. But then introduce white noise, of course, nobody wants noise in your data. So everybody wants to get rid of the noise. So once you introduce noise, how can you take the noise away, eliminate that? So by elimination, to eliminate this white noise, is that you just keep doing it. You do it once, you do it twice, then the noise cancel out each other. So finally, what you got is should be the correct answer. So this is the rough approach. So the background one is, let's review intermittency. To avoid mode mixing, we instituted a special criteria to separate oscillation of different time scale. Yeah, the criteria is to select the scales so that anything longer than that, I will ignore it. So I only get the shorter ones first. Yeah, the shorter ones may not be everywhere, but I will get it out. Once we get it out, I will not mix the short one with the long one. The first time I get it, it's all the way shorter than the criteria that I got. You can start from very, very low values, like 2 points from extrema to zero crossing. That 2 points means that the whole wave has 3 to 4 data points. Those kind of waves most likely are noise. Even if it's not noise, the instantaneous frequency you get is not very meaningful. Let's sit over here. Yeah. Maybe I will block you. Perhaps you should go there too. All right. So, intermittency tests, as I said, made the mode mixing less serious. But intermittency required subjective criteria, destroyed the total adaptivity, and the most serious problem is perhaps the last one. The last one is that how do you choose this criteria? In simple data, it's easy, but in complex data, the scale may be continuous. So where to cut off? That becomes an issue. But then we can, so this was one of the shortcomings that we identified. However, when you consider any other method, like even if we introduce white noise also has the same problem, the so-called dyadic separation. But this dyadic separation has overlap. This has no overlap. It's very clear cut. It's shorter than anything I will take, longer than anything I will ignore. Yeah. So this is a much severe condition. This whole idea of EMD is to separate data into different similar scale, get rid of the riding wave, make the result symmetric. Yeah. But by making the symmetry, we actually destroy some of its physical property. We don't know the data should be or should not be symmetric. But the reason that we want to be symmetric is because we want to compute the instantaneous frequency, right? So that is, we force the data into that mode. So that's intermittency. The second thing is the theoretical study of the white noise. And this actually is the foundation of the ensemble EMD. And this study actually is published in the Proceedings of Royal Society in 2004. It's a very interesting story. In the data analysis community, there are several very well-known personnel. One of them is Patrick Flandre. Many people in EE knows about him, right? I don't know, 你们知不知道 Patrick? Yeah, Patrick. Patrick, I think he's one of the best data analysis person. He's from Lyon, École Normale Supérieure. École Normale Supérieure was established by Napoleon. Yeah. At that time, they find that the university professors are not uniform, without a uniform quality. They said, all right, we're going to train some of the best teachers for the university. So they established École school, normal school, I mean 师范, normal, superior, the highest. In France, you can go to, if you graduate from high school, you can go to any university, but not the few selected one. École Normale Supérieure, you have to pass the examination. It probably take 200 each year or something like that. Yeah. So very, very selective. He's a professor over there. He's now an academician in French Academy. It just get inducted last June. I first met Patrick was in 2000 or 2001 when I visited Cambridge University. He was there. He was there in the Newton Institute, talk about non-stationary, nonlinear time series analysis. So I went there and presented my method. Nobody was impressed. They said, well, your method is no good. You don't have any theory, and you don't have any assumptions. And this is just a method to use a word ad hoc. Just get the answer. That's it. Later, I met him again. His attitude didn't change. Then about 3 years later, about 2003, I got a paper to review. It was by Patrick. And turns out, at that time, he started to use empirical mode decomposition. I will later discuss this paper. Meanwhile, just before that, Zhaohua Wu, Professor Wu came to me. He attended one of my seminars, and after the seminar, he applied this method to white noise. And he got some interesting results, and he showed it to me. I said, well, this is good. Why don't you write it up? He didn't do anything. A year later, when I get Patrick's paper, it's also on white noise. So I find the two are very similar, but not exactly the same. So I got Zhaohua's permission to send his manuscript to Patrick, and get Patrick's permission to show his manuscript to Zhaohua. So then Zhaohua, after discuss with me, immediately wrote a paper to Royal Society and got accepted right away. And Patrick's paper was also published in the IEEE, I think. Yeah. So from that time on, Patrick come out of his lab and start to use this empirical mode decomposition. The methodology is that we use Monte Carlo method to apply to 1 million data points of white noise. And then all the IMFs are generated by 10 shifting. The stop criteria is fixed number of iteration, 10 times and stop. Whether it's done right or wrong, stop at 10. And then we also done some Fourier spectrum. Fourier spectrum is based on 4,000 points. It's 200 realization. The probability density function that we talk about, each one is generated by 50,000 data points. So what is the most important, most shocking result is that if you give me 1 million data points, and this 1 million data points, if I go through empirical mode decomposition, what you find is that the first component has this many peaks. And so the average distance from peak is 2.88 points, the average. The second component has that many peaks, and average 5.9. And then the third is 11.98. So this 5.9 is almost 6. Yeah, 6 double, it's 12. 12 double, 24. 24 double, 48. So from a white noise using EMD, you actually get out the kind of the answer is exactly double, exact dyadic. And that's what made Patrick Flandrin called EMD a dyadic filter bank. Yeah, it's filtered the data by dyadic means twice, each time is twice. You look at this, it's really shocking. 24, 48. 48 is 96. 96 is 100. 196, 100, 92, yeah. The difference is so small, it's less than 2%. Yeah. So, and not only that, if you take those components, you plot the Fourier spectrum. Yeah. The Fourier spectrum looks like this. Each one looks exactly like the other. Yeah. But all center at different peak frequency, except that there is one slightly off. But if we normalize this into one, then we can make every one stack up. So you take the peak frequency, fix the peak frequency. You can actually plot all the spectrum into one. In other words, all the spectrum, the area covered under the spectrum is the same. If we integrate this is log, by the way. This is log scale, log frequency. So if we plot log scale, they are all the same. Then we can normalize it in log t. They're normalized to be the same. And this is very interesting. The interesting thing is that the energy density is actually the square part of that, of the square, summation of square divided by the total number. But this is the way that we compute energy in time space. But if we compute energy in frequency space, the frequency space means the spectrum right in terms of log t, yeah, and the integrate will be constant. That means this area is constant. Each one, if we use log t as base, the integration is constant. Yeah. This result has very interesting implication, and we'll see what it is. So, energy density, by definition, is a spectrum integral. Spectrum integral equal to RMS, right? So that's Passivhaus law. So now let's see. Spectrum equal to energy density equals to spectrum integrate. This is frequency. Now, what if we change frequency to time? Frequency change to time by the rule, by the variable change. Frequency equal to 1 over t. So if we change 1 over t, d omega equal to dt over t squared. So the d omega becomes t over t squared. So then this is the same thing. Yeah, but this is over t. But what if we change this from t to log t? Yeah, we change t to log t. D log t is our new variable. D log t is dt over t. So then one of this t becomes d log t over t. So then this becomes variable in d log t. All of this are identical. They're just variable change. Once we get this, we invoke mean value theory. Yeah. The integral of this is integral of this whole thing equals to a mean value of some t. Yeah, equals to this integral times this one of this particular t. Yeah, this is mean value theory. So if that's the case, then just think, if I multiply this capital T over to n, what I got? I get log integral of sine log t n dt. But this we have already said, this terms equal to constant. So after this series variable change, E times T bar, T min, becomes constant. Yeah. Now, if E bar times T equal to constant, So I take log, log E plus log NT equal to constant. So this whole thing comes from the integration of the spectrum equal to constant. Then we immediately get this. And this means that you can plot all your components. And the components, this is plot log T, this is plot log E. Because log E plus log T equals to constant. So this line has to be -1 power. Yeah. So this is a very interesting result. You see all the data are all lined up along this line. Yeah. But along this line, this is the average. This is the average. They are scattered up around this. Yeah. So this result and this result was obtained both by Zhao Hua and by Patrick. In fact, here is where we diverge. Patrick, he studied all kinds of noise. White noise is only one. We use only white noise. White noise gives us the -1 power. This is -1 power. What if you don't use white noise? I use brown noise, I use red noise, I use all kinds of noise. Then Patrick studied all colored noise and find the slope is not exact -1. Sometimes it's steeper, sometimes it's shallower. Then he claimed in his paper, later we'll talk about, that we can tell what kind of noise you encounter, whether it's white noise or not white noise. If it's -1, it's white noise. If it's not -1, it's not white noise. Zhao Hua, however, went a different way. I think this different way is much more profound, give us more appreciation of the method. He started to study the distribution. Excuse me. Started distribution, and he found that the distribution of each component is actually normal. Yeah. From component number 1, it's very poor because component number 1 only 2 or 3 points per wave. From mode 2, 3, 4, 5, 6, all the way to mode 9, they're all near normal. Now this is another interesting thing. Then, if we find the distribution of something which is, if we know the distribution of x, then there's a fundamental theory that we can find the distribution of y, which is a function of x. Yeah. So, Zhao Hua find the distribution of x is normal. Then we should be able to find anything of that. It's straightforward to find the x squared distribution. But instead of that, Zhao Hua now wants to study the, the degree of freedom of each component. And that means that given any normal distribution independent random variable like this, each one is normally distributed. And in our EMDX expansion, C1, C2, C3, each one is normally distributed. And the question is, how about the sum of this? How is the sum distributed? Yeah. So if you go to Populus, you will find the sum can be written as a chi-square distribution with new degree of freedom. The degree of freedom is a very important statistic quantity to determine whether a distribution is believable or not. What is the degree of freedom? That means when I determine something, how many ways you can change. Like along a line, the position degree is 1. Along a surface, the degree freedom is 2. I can move either x or y. Yeah. Position in the space is 3, and so on. In data, each point I move to next is a degree of freedom. I can move my next point to any point. It's a random number. So the number of data points is degree of freedom. And in Fourier analysis, each wave is a degree of freedom. This next one, I can be arbitrary. How about the degree of freedom of this? There's no definition. So Zhao Hua tried to find the degree of freedom. If you guess the degree of freedom right, you can write this whole distribution of y in a chi-square, and Zhao Hua proved that the degree of freedom can actually be a chi-square distribution. But how you define the degree of freedom? Let me see, chi-square density. I have a slide to define degree of freedom. Okay. The degree of freedom, this is something I think Zhao Hua did very nice. He says degree of freedom actually is proportional to energy. Yeah. If the energy is stronger, means then this degree is this determine the data property more. So then he assigned more more degree to that. And once you assign this degree of freedom proportional to energy, then you can write this out as a chi-square distribution of this nu. Yeah. Once the chi-square is nu and he used the data, he actually proves that indeed the distribution is almost the distribution is indeed a chi-square distribution. With this chi-square distribution, then he will be able to manipulate this. This is the degree. This is chi-square. This nu, if we use this definition of degree of freedom, we can write it as n times e. Yeah. Now, once you write n times e, this becomes the chi-square distribution. Then, by fundamental theory, I know the distribution of that. Then I should know the distribution of this. So you make a variable change. You call the new variable ne because n is constant, the n comes out. The reason the n comes out is that your new variable is now ne. But this is constant. So this is a new variable. So new variable, so dx becomes n den. So this n, the only thing come out is over there. Everything else is the same. Then you made another variable change. You write e as ey exponential y. So you write all this e as y. E bar is constant. E bar doesn't change. Okay. So then you can reduce it down to ne times y minus e over e bar. Once you get this form, you can immediately see that this form is the same as, indeed, it is the same, just different variable. And you can, again, if e equals y, then y equals log e, then you can substitute this back in, and the only variable is this term. Yeah. Now, e over e bar means e is ey. E bar is minus ey bar. So this exponential can be expanded as the first term, the second term, the third term, Taylor series expansion. So you can plug back into there. Yeah. Once you plug back into there, then you notice that this is constant, can be factored out. Yeah. all of these parts are all are all constant, and and this y will eventually cancel by that y. So the leading term actually is that term. Yeah. So through this manipulation, because this is constant, this is constant, this whole thing can be absorbed into a new constant, and the leading term will be that. So the leading term actually is a distribution, almost normal distribution. Yeah. Now, once we get this, then we will show you that the distribution, if you make it approximations look like that. If you do not make approximations, it looks very nice. It covers the whole distribution of the all the cases. But then instead of stop over there, what Zhao Hua did really brilliant thing is that he wanted to find out how far away is the confidence limit that we can establish this distribution. So the confidence limit is that the total distribution from -infinity to infinity to a y alpha, if I integrate instead of the whole thing, I stop at the alpha. The value is not infinity. Like I stop at the 3 sigma. I stop at the 2 sigma. I stop at the 0. Yeah, mean. So by select 1%, 25%, half, 75%, 99%, we can get this y bar for normal. We can get it as a -2, -0.667, or 0 is the mean, which is 50, and then plus this. This is 1 sigma away in the normal distribution. Many people use this as an important criteria. That's 1 sigma away. Means 67%. Using this, then we can establish this alpha value, and then this is our definition of the standard deviation. And the standard deviation we can write in different form, and then make the variable change of by selecting an alpha value, which is given here, depends upon how large you want to be. The alpha can be alpha is a variable that you can choose of this. And this alpha means you get a 1% or 25% or mean. By choosing that, then you can rewrite this alpha into, you get the whole confidence band. The confidence band actually eventually can be written like this. And plus minus will give you x. This x is defined as log t, y is defined as energy. So on energy and time space, you can establish, depends upon your k, you can establish the confidence. And that confidence, you can plot it over on this. And that actually gives us a very good method to check the statistic significance of the data. If the data, for example, if we choose 99% over there, if the data falls in here, then it's possible it's noise. If the data falls out there, all the white noise should be within this boundary. That means this is not noise. This is a statistical significance. Yeah. This deviation between Zhao Hua and Patrick in this is that Zhao Hua actually studied the statistical significance of this, and Patrick studied the slope of that line. Yeah. So the two are complement to each other. So, for example, if we take the data, we expand it out. This is actually the Southern Oscillation Index, which is actually the data in the oceanography field. It's the pressure difference between Tahiti and Port Darwin, which is closely related to El Nino events. If you plot this, then you find that depends upon where you put the first one. And if you put the first one high, you get the upper. If you put the first one low, you get the lower. But whichever way you do, these 4 data points are above the 99th percentile line. Yeah. So means this data, all the other data may be noise, but these 4 components are not noise. It turns out, if we look at this component 1, 2, 3, 4, the fourth 1, 2, 3, 4, this start to be almost twice yearly, which is El Nino events. And then you also get almost about 5-6 year and decadal, multi-decadal data. In other words, this part are significantly non-noise. So in this way, when you get your answer, you don't use every component. You don't try to understand every component. Because some of the components may be noise. Yeah. Maybe noise that you cannot tell the difference between that data or noise. All the data contains noise. How to separate this noise from the data? Yeah. From the information. That's the important thing of our analysis. In this way, then we establish there are only 4 components, which is above and beyond, above and beyond the noise level. 99th percentile confidence that is beyond noise. So the summary is not all IMF have the same statistical significance. Yeah. Based on the white noise study, we established a method to determine which component is statistically significant. Yeah, this is really beyond my original imagination that we can not only decompose, we can also establish the statistical significance of the data. Now, so the white noise consists of all scale. EMD separate scale dialectically, and so white noise actually gives us a very interesting thing that we can separate the scale uniformly. And then, as I say, Patrick in 2004, he also published his empirical decomposition as filter bank, and then he applied this filter bank to interpret the signal. And what he did is that at the very beginning, he does not want to just study white noise. Zhao Hua wants to study white noise and have found application. He said no, he wants to study the so-called fractional noise. White noise is one kind of noise. Spectrum is white. And what if my spectrum is more red? I have higher noise content even than white noise. Yeah, this is, all depends upon the slope. And this is the way to generate all kinds of different colored noise. It's called fractional noise. H is a parameter known as Hurst index. A Hurst index is a way to study fractal. If you look at any fractal book, you'll find that the Hurst index come up. What he did was he studied the flood level at the, along River Nile in the reservoir, and he found that the fluctuation of that actually is not totally random. Anyway, so if H equal to 1/2, if here H is 1/2, you give you Gaussian Brownian motion, which is white noise. If it's a large white noise, it's more red. If it's less than white noise, it's more blue. Yeah. So red means you have more longer wavelength, and blue means you get a shorter wavelength. So here is H equals to 0.9, H equals to 0.55. This kind of data all have much longer wavelength than white noise. Yeah. So by change this, you actually get a different kind of noise. So then he studied each noise. He studied noise equal to 0.1, which means much more blue. And then you find that this is the spectrum of each component. You find the spectrum of each component. At 0.1, it's slightly off. After that, the spectrum peak all aligned with this line. This is white noise. Means all the spectrum are all the same height. Yeah. And these are more blue, and these are more red. Yeah. Every spectrum are along the same line. So then he noticed that because of this line slope change, he said, aha, I found a way to tell the noise, whether it's white noise or not white noise. More red, more blue. So because he used to study this, and his direction is going to separate the noise. And indeed, all the spectrum can be normalized, just as Zhao Hua did for the white noise, which is this case. And plot that slope of number of IMF, yeah, log 2 energy, and the number of IM, which is scale, but you actually get a slope. This is slope. This is H parameter. This is the slope. You find that this slope actually gives you a very good indicator of what kind of noise you got. And that is basically what Patrick did in his 04 paper. Yeah. And later, after he have seen what Zhao Hua did and established the confidence limit, he then numerically reconfirmed what Zhao Hua did. This is 95 percentile, 99 percentile. This is mean in the data. So this is the theoretical model, and this is what he got with data. So they compare theoretical model with a few deviations. So it's confirmed very well, give you the error bar. So this study of white noise gives us a lot of good things. The first one that we can see is to give us a confidence limit of a result, and a tool to statistically test whether the data, whether the signal has significance or not, has meaning or not. If a data has some signal, has some meaningful signal, this is actually a meaningful signal plus a noise. Yeah. So you put this together, you can separate this signal and noise. And when you plot out the components, what you got? The components, component 1, 2, 3, that the signal you got is over here. So in other words, this is way beyond 99 percentile boundary. So this is a statistically significant signal. Yeah. So this is this is his way to confirm what Zhao Hua did in the significant test. Yeah. He also used this to study the delta function. See, delta function, what he did, the delta function using the straightforward EMD is impossible to decompose because there's only one extrema. How are you going to do it? So what Patrick did was to add a little bit noise to it, a little bit. Yeah. After you add a little bit noise, then you find that this signal actually come out to be expanding. So this was one way that people say, what if my data has a jump? Yes, your data has if your data has a jump, the jump is not going to be local. No method can give you a local answer for a data jump. No method that I know of so far, especially in time frequency domain. If I give you a delta function in Fourier space, what do we got? We get a white. That means this delta function influences every place. So in Fourier space, is local in time means frequency uniform. Frequency local in frequency means everywhere in time. Delta function in frequency means a sine wave. It's everywhere. In wavelet, it's confined. In HHT, it's confined. The confined means my influence is spreading out. It's spreading out slowly. Now, this spreading looks bigger and bigger, but actually all of this form can be normalized to that. Yeah. So that's why Patrick, as I said, Patrick is one of the greatest data analysis person. Data analysis community we divided into two different camps. One prior to HHT. One camp is to do wavelet. Another camp is to do Wigner-Weil. Okay? If you read the Wigner-Weil book, they will never mention wavelet. If you read wavelet book, they will never mention Wigner-Weil. Patrick is the only person in one book talk about both. Okay, so not only he talk about both, he talk about HHT also in terms of wavelet. This is HHT is a dyadic wavelet. Yeah, it's almost like a wavelet. So we're almost ready to jump in to the ensemble EMD. Except there's one more. It's the effect, add noise to the data. What's the effect? Yeah. And this was studied by Gledhill, Robert Gledhill. Gledhill is the Department of Chemistry. Yeah. He is, his thesis is very interesting. His thesis advises Essex, Professor Essex. Professor Essex, his research work is looking for new drug, specifically new drug for mad cow disease. Yeah, mad cow kind of disease. What's mad? That is the mad cow disease, 疯牛病. Mad cow disease means it's a totally different kind of disease to anything that we know. A disease usually generated by germ, by virus or by your body change, like cancer or whatever. Mad cow disease is a third way of, not from germ, not from virus. It's from small particle of protein. This small particle protein usually exists in people's brain. And when you eat animals' brain, you ingest the small white particle, the pion. That pion is a small protein will go in your body, and when you get it to your brain, that pion will lodge into your brain protein. Your protein is a very complicated structure. When you lodge it with protein, you change the property of the protein. The vibration totally changed. And not only to change that protein, it becomes a catalysis to change all the other proteins. So then your brain, instead of uniform white gray material, becomes spongiform. So the mad cow disease is called the spongiform brain disease. Yeah. So they want to study that. They want to study the protein vibration, and they found which vibration, which part actually is been damaged. Yeah. Now, if you can find which part is damaged, then you can find a medicine to either unjam that or to strengthen that particular joint to make this protein particle will not cause the damage. Now the people, mad cow disease, cow should not have that kind of disease because the cow is vegetarian, it only eat grass. Where do you get this protein? It turns out that the cattlemen, the people raise cow, found a very good way to make the cow, make the beef tasty. Yeah. How to make it tasty is the cow has to get fatter. You only eat grass will not get fat enough. The beef will not be tender. So before they slaughter the cow, they want to fatten up the cow. To fatten up the cow, they feed the cow some good stuff. This good stuff is actually generated from the waste of the slaughterhouse. So when you slaughter the cow, you only harvest the useful part, which is the beef. You get the beef away. All the rest, the brain, the intestinal, whatever, they all grind up, dried up, and then mix with the grain and feed back to the cow. Turns out the cow likes it. When cow ingests this fat, the cow getting fat. And getting fat, the fat getting to the beef. The beef looks like a marble. And that is tender and tasty, and you can fetch higher price. So the cow started to eat cow. And that's how the protein gets to the brain. Yeah. And the first one discovered this disease is by observing the Aboriginal people in New Guinea. They have a strange custom of eating up the dead person. If the ancestor, if your grandfather died, they threw a party and roasted the dead person and everybody eat it, including the brain. And that's how those people get this mad cow disease. Yeah. So they are doing that. And they're trying to study the vibration of protein. And they cannot find out which vibration, which joint is bad because it's so local. They use wavelight, they use nothing worked. And then finally they use HHT and worked. This paper was published in this paper was published in a biochemical journal. And this person did a very, very thorough job on HHT. He finds that when you apply EMD, you may get, one time you may get one answer. You slightly change the data, you may get another answer. So he wants to know what's going on. Yeah. So then he assumed that if I add a little bit noise, I'll perturbate the answer. then how much noise can make the answer unstable? So you studied the stability of the method. So by studying the stability of the method, obviously a basic assumption is that the correct answer is the one without noise. Yeah. Anything you add noise, it's perturbated. So he wants to study the discrepancy of the answer with different kind of perturbation. And what he finds is that depends on how you add the noise, the amplitude. This is a log scale of the noise that you add. This is 1 means the noise and the data is the same height, same magnitude. This is 1,000s, 100s. And he found that if you add a little bit noise, it doesn't matter. But when the noise is much higher, then the discrepancy becomes big. Yeah. And this case is that if you add a noise to only 10% of the data, not the whole part, the small part has been perturbated. And notice that this scale is different, okay? This is 0.02, it's here. Yeah, so if you only add a small part, by the time you add it to about 1,000th, it starts to give you perturbations. So that means the data, if the data has noise, it depends upon the signal-noise ratio. And he studied millions and millions of cases. This guy is really in this very early time. And he finds the discrepancy, actually, this is the noise level, and he found the discrepancy actually increase with noise. This is not very surprising. Yeah. But it's not always this. There are some bimodal distributions that he got. Sometimes it's very stable, doesn't matter. Sometimes it's this. Yeah. So in this way, then he concludes that the EMD is stable if the noise is less than a tolerable, like a 1% or 10% or whatever. So by doing different kind of choice, different try on the data, then he can deduce what kind of noise is involved in the data. This is a totally different study. Yeah. So this result, they almost find the ensemble EMD, but because they made the critical assumption that the unperturbed signal gives the correct answer. Turns out the unperturbed signal may not be the right answer because you don't know the original data has noise or not. Yeah. It's only one of the possibilities. So the amplitude of added perturbation is small, the distribution is small, of course. When you add large perturbation, it becomes bimodal. And this actually puzzled him. So why is it bimodal? Bimodal, yeah. So this people has studied noise together with the signal. The ground is almost ready for ensemble EMD. And we will talk about the ensemble EMD next session. I think my voice is already to the limit. I'm going to stop today, right here, half hour early. Yeah. Next time we'll talk about the EMD method itself. Okay. Any questions? Hi. We're going to stop this class early today because my voice cannot hold on to it. Okay. We'll see you next time.
Please
right.
take care.
Right. All right. 好，你们有没有什么问题？这个有问题我们还可以 discuss 一下子，要不然我要这个我们 class 也就 over 了啊。对啊。
刚好提到那个 degree of freedom
啊。
这个参数呢，是在有什么就是用处？啊。是在决定 IMF 的个数，或者说是决定
不，跟 IMF 个数没有关系啊。这个是totally different 的 concept。就是他们这个 statistician 你常常得到一个 answer， 那这个 answer 你知道这个 answer 有多可信啊？比如说我们现在做的这个 climate change， 就有很多人来问我们的 climate change 这个 climate data looks like this 一直上去，那我们呢现在得到一个这个 wave， 所以你假如你只得到一个 wave 的话 ，how do you know 是一个 wave？ 那么你这一个 wave， 好比说我假如要是得到一个 wave 又拉 after wave， 那这样我就说这个是 periodical。那我假如得到一个 wave， 你说这个是 periodical， 我相信这个是 periodical 的可能比相信这个是 periodical 的可能要强得多，对不对？那这个 periodical wave 比这个 periodical， 为什么你相信这个？因为这里有好几个 wave， 所以在这个 analysis 上，每一个 wave 就是 one degree freedom。所以这个呢，我1、2、3、4、5、6，我有6个 degree freedom。这个呢，你只有 one degree freedom。所以 degree of freedom 就是给你 confidence， 并不跟那个 IMF 的个数没有关系。你 degree freedom 越高，就表示你越确定。
所以说在做那个 white noise 分析的时候，还有那个 degree of freedom 是保证你那个在做 white noise 分析的时候可信度。
不 ，degree white noise 在 white noise 里面，我们唯一用 degree freedom 是把它的那个distribution 从那个 normal 的，就是从它的这个 amplitude 的这个 distribution 换到 chi-square， 换到 chi-square 里面就引进来一个 degree of freedom， 就是说你这个 distribution 多可信。chi-square 是一个 test 可信度的一个 distribution。可信度在 statistics 里面有好多办法，什么 student t-test 这种各种各样的这样里面都多多少少引进了这个 degree freedom 的这个 concept， 这个是完全是 statistician， 他们要 judge 这个 result 多可信得到的。那么从这个 normal distribution 变成它的这个 normal distribution 的平方，就是因为我们找它是 energy distribution 多可信，这个时候呢就引进来一个 degree freedom 的 concept， 是跟我们的 number of IMF 什么都没有关系的。那么在了 IMF 里面，你怎么样去定它多可信它的 degree freedom 怎么定的？吴兆华用了 energy 的 argument， 就是 energy 越大越可信， energy 越小越不可信。那么从它这个 assumption， 就是它的 degree of freedom 定成 n times e。sorry。degree of freedom define 成 NE， 这个 definition 就已经告诉我们最后的 distribution， 这个是 log E， 这个是 log T， 对吧？所以这个已经告诉我们，就是说 energy 决定可信度，因为它这个上面是在 energy 外面的一个包的一条线。 对不对？我 energy 大的话就是可信，energy 小就不可信。啊，所以有了这个 assumption， 已经一定会引到这个结果，就是在 EMD 里面大的 energy 多的就是有 information，energy 少的就没有 information。那么假如你是 white noise 呢，那越长的尺度 energy 越小，啊，所以你要又长尺度 energy 又大，所以你假如得到一点在这里的话，一定可信，因为假如在 white noise 的话，它应该在这里，那它不是 white noise， 所以这个整个的这个只是告诉我这一个 component 不是 noise。那么多不是 noise， 多可信呢，就看你这个大多少，啊，所以这个说穿了，它的整个思想就是说，我分了以后啊，我就看你大小，越大的我也信，越小的也不信。说白了就是这么一句话。但是呢，大小你怎么比呢？大小要比在这条线上来比。这条线什么？这条线就是那个，就是我们在。他把我挡住了，不让我去。呀，这条线就是 x y， 这个 x bar minus y 就是这个，对吧？我这 x 等于 t bar 啊 ，y 等于 log e， 呀，就是这个 x y 就是这条线 ，x y 就是这条线。我剩下要找的，这是 x minus y， 这个是我的，这个是 white noise， 这个是 white noise 以上的 distribution， 呀，这 distribution 呢 depends on k， 你要多大几%来挑，你挑的 k 是95% 得到一个 value， 你挑的 k 等于say 25% 另外一个 value， 呀，所以这个 k 决定你这个开的多大多小，呀，那么 x minus y 就是这个当中这条线，呀，那么因为有了这个假设，所以我们最后的决定就是 energy 决定，别的不管。
N 的话就是资料的长度。
对 N 是资料。OK。
还有一个好奇是说，这个 N 跟1的关系，好像跟我们的场次是一样，就是资料越长，然后能量越大，它就越好。
对，你资料越长的话，你越可信。对。呀，因为你资料我只有3点，或者只有20点，就很难取信，对不对？你尤其是越到这边来，它这个 wavelength 就已经很长了，呀，这个它的 energy 就变得非常非常小，所以你真正的 wave 说不定只有2个 maximum， 你怎么去相信它呢？就是你要非常非常大，我才能相信。一般的数据啊，所以我现在就跟这个很多，现在好多东西我自己也没有想通它，我假如想通的话，就会，这个要做很多 research， 比如说我们现在看的一般的物理的数据，差不多都是这么分布的，就是越长的 energy 越小，不是 energy 越大，但是反过来不是物理的数据，是什么呢？股票。对啊，那股票啊，越长的 energy 越大。股票一摆到这个 EMD 里面去做，它那个你做 significant test， 每一个 component 都是比那个都是大，对啊， 所以我认为股票每个 component 每个 cycle 都是 significant。可是做股票的人，现在做股票的人，因为股票就是 white noise， 是吧？他们的那个股票，现在拿了诺贝尔奖金的这些人，也是认为股票就是 noise 啊，它叫 ARMA 啊，就是 moving mean， 这个auto regression moving mean， 但是他知道 auto regression moving mean 一定是乱七八糟就不行了。他说我把它 integrate 一次，因为你假如不 integrate 的话，它是乱走的哈 ，integrate 就变成那个 random walk。它也会走得很远，会下来走得很远，但是你不要想，用不着非常聪明的人也会想到这个是不对的啊。这个不对的有好几件事不对的哈，但是这个第一个，这个股票它是有走向的 ，ARMA 没有走向，对吧？它最后是 zero mean 的，这怎么办呢？他这个玩股票的人很有意思，所以我跟你讲，你们千万不要信那些玩股票的人。他们玩股票的时候，我不要看股票，我看什么？我看 gain。什么叫 gain 呢？就是我拿这个股票去 take log 股票的价钱，value v， 然后呢，我把这个东西微分一次，叫 dv over v， 我就 start 这个 variable。这个 variable 我今天跟昨天的价钱的比，除了当天的价钱，完全看 gain， 完全看它的这个大小。它这个就是 white noise 啊，这是不是 white noise？Heaven knows， 我还是我想也不是，对吧？虽然它是变得几乎 almost zero mean， 因为这个 dv 啊。是一个 linear operator。假如你做底位的话，这个在谱上面讲是非常简单的一件事，对吧？谱的 dv 就是欧米伽平方乘上去就完了，对吧？假如用这个 spectrum 来看，就是欧米伽平方乘过去，但是它除了一个 v， 这就麻烦了，对吧？这个 operation 就已经不是 linear。这个 operation 就比较麻烦，所以他们现在都在玩这个 game。所以这个看这个 significant 是跟它的 degree of freedom 有关的。我们从 degree freedom 的 definition 引进来的这个 concept， 有了这个 foundation。我们最后的 conclusion 就是你不要看这些 operation， 这些 algebra 都不要去看它。就是说我假如 make 那个 assumption 后，我的 consequence 什么？大的有理，小的没有理，对不对？讲白了就是这么一句话。你要说你是 significant， 你一定要有 energy， 没有 energy 是 value。OK。还有没有？没有，那我们今天不讲了啊。